Excited for this slate of talks. Quick update on the schedule for tomorrow. Tomorrow we'll start a little later, so coffee will start at 9 a.m. And at 9:30 a.m. we'll just have like a short 15-minute little block of closing remarks before Theodoris's talk. And really excited about the workshop discussions this past week. I think with our closing remarks, we'll talk a little bit about paths forward. What does infrastructure look like? Hopefully, start some ongoing discussions about that. So, without further ado, we're super excited to have Jann Spiess give a talk. Spiess?
Spiess, yeah.
Spiess. You should ask him for a better pronunciation. Jann is an econometrician in the OIT Operations Information and Technology group at Stanford GSB. His research focuses on high-dimensional and robust causal inference, as well as data-driven decision-making with misaligned objectives. So a lot of really interesting projects. It'll be great to hear from him about this.
Thank you so much. Thanks for having me. So I'm presenting some work today on estimating heterogeneous treatment effects and using that information for targeting. And this is joint work with Susan Athey and Neil Killer. So we run an increasing number of very, very expensive randomized trials across the social sciences that often cost millions or tens of millions of dollars and are mainly used to estimate average treatment effects. And so the availability of flexible data-driven methods, specifically for machine learning, bring a promise with them that for those very extremely, for these large randomized trials, we may be able to move past just estimating average treatment effects, but instead we may be able to learn about heterogeneous treatment effects and whether an intervention works for specific people better than for others. Let me just give you some very concrete examples of the randomized trials that I've been involved in the analysis of. So for example, there's a BCFG gym study. This is work by Katie Milkman and co-authors, where we are basically asking not which interventions get people to the gym, which is what the original experiment is, but instead we're trying to shift that question towards taking this randomized trial in which different strategies were randomized that were supposed to increase gym attendance towards the question which of those different interventions works best for whom, so that we can then go ahead and target that. Or in an ongoing project with Jens Ludwig and co-authors, we're currently trying to evaluate the effectiveness of tutoring to get students to catch up on learning. Tutoring, however, is very expensive, so it's a very relevant question to not just ask whether tutoring works well on average, but instead for who tutoring works and whether we can use that to target students better. And then finally, the example I will have for you today is going to be an application to nudges in an education context. So here we're using some data from an experiment that was run by Ideas 42, and they wanted to know whether they can nudge students to renew their student financial aid applications in time. And so rather than asking the question whether this worked on average, what we're going to focus on today is for whom the reminders are more effective and whether we could have used that information to target those reminders better. So what is a challenge that arises with this randomized trial, but also with many, many other randomized trials in the social sciences that we have worked with? Well, in practice, many of those randomized trials are actually quite small and have quite noisy data because they're typically powered for an estimation of an average treatment effect, and it's not that trivial to estimate heterogeneity in them. And so therefore, in my talk today, I will focus on specific approaches that help us to nevertheless get some information about heterogeneity out of those relatively noisy trials. So I will first present the kind of standard toolbox on causal machine learning to estimate heterogeneity. I will then argue that here this is unfortunately limited because things are very noisy, and then instead compare a number of strategies that try to still work by combining some predictive inference where we're thinking about targeting not based on some causal estimate, but just based on a prediction of baseline with these causal models. And so just to very briefly preview the empirical results from this one experiment that we think actually generalizes to similar experiments, we do find some heterogeneity, but it's extremely noisy. And as I said, it's an experience we've not just made in this randomized trial, but in many that we looked at that we try to reanalyze. And so in this specific case, one effect of this is that targeting based on the standard causal toolkit works, but it's extremely inefficient, while targeting based on combining machine learning for simple prediction tasks together with a causal model does much better. So where we are combining a simple economic model with some non-parametric machine learning, that's better than just using the fully non-parametric toolkit. And then the first point that is on this list here is also that if we instead took a total non-causal approach, so we targeted just based on prediction just based on something that we would have done without any understanding of the causal relationship here, we would have actually done much, much worse than any of those approaches because we would have targeted the wrong people. And I'm going to get into more detail about what I mean by that. So that's a quick overview. I just want to point out that, of course, we are contributing to a very active literature on heterogeneous treatment effect estimation here in statistics, causal inference more broadly, econometrics and operations, as well as in computer science. And so just mentioning that we're building on this literature here. Specifically here, I'm going to build heavily on previous work by my co-author Susan Athey and my colleague Stefan Wager. So what is the specific context that I'm talking about today and the specific data I have for you? So we are talking about targeting a nudge intervention to students in the CUNY system in New York. And specifically, the main analysis here will use a sample of 25,000 students that come from 3 community colleges in New York that are randomized 50% to control and 50% to a treatment intervention that I will go into more detail of. We also have some additional data from 2018. So the background here is that in 2017, it was found that this intervention was effective. And then in 2018, there was a follow-up randomized trial to try out different versions of the treatment. So the 2018 trial has more students, however, also has a much smaller control group. So for our purposes, I will just focus on the 2017 data. The covariates we have are over 100 baseline demographic, academic, and administrative data for each student. So for each student in our sample, we know something about their demographics, but also about their school performance, like basically how many credits they have taken, what their GPA is, their enrollment status in past semesters. The outcome that I will be interested in today is whether the students renew their student financial aid FAFSA by a priority deadline. And so the idea is that many of those students are eligible for federal financial aid, but in order to get that federal financial aid in time to continue studying the next semester, there's a priority deadline by which they're supposed to hand in their application. And so our goal is to maximize renewal by that deadline so that we make sure that students renew. Now, here's, I think, a first limitation of this data. We would love to have some follow-up data on, say, graduation rates, because it's generally believed, and there's some data on the fact that getting access to student financial aid makes it more likely that students graduate. In this case, we only have this, what I think of as an intermediate outcome of whether they file by the deadline, but not necessarily about when they end up receiving their student financial aid and what the effect on graduation is. So we're going to use this simpler proxy here in order to represent those things. So what's the timeline for the data I'm about to show you? So we basically do two data pulls. We first get a timestamp data that is the data that would have been available before the start of the semester that has the intervention. We then do a second pull that kind of is before the intervention, but maybe in realistic applications may not have been available for any targeting. So this is to add some data about, is the student actually enrolled this semester, for example. Then the intervention starts. I'm going to go into detail what that is. The priority deadline passes, and afterwards we get the information of whether the student renewed by the deadline or not. And so what is the intervention? So the intervention is a typical nudge that tries to get students to renew their student financial aid by using some behavioral tricks in order to make it more enticing for them or make it more likely that they renew. So specifically, it's a series of sometimes personalized text messages. So they're not just getting one of them, but they're getting all these text messages relative to a control group that just gets standard emails. So you can just like pick one. Number 3, for example, says, renew your FAFSA today. Many people renew in 30 minutes or less at this link. Tip, use the IRS data retrieval tool to renew quickly. So the idea is like, I'm telling you this is easy. You should do it now. Other people are doing it. I'm using some kind of tricks from the behavioral science literature here to make that more likely. And by I do that, I should say that this is Ideas 42 had already run this trial when we started working with them on that. So we are retroactively analyzing the same data. So what is the baseline analysis that had already been done here? So the baseline analysis is to use this randomized trial where people were randomized into whether they got this set of messages or not, and checking whether there was an average treatment effect. So in this case, the intervention increased renewal by the priority deadline by around 6.4 percentage points. So this is against a baseline of, I believe, in the 30%. So later on, I can show you the exact numbers. So you may ask yourself whether this is a large treatment effect or not. And I would say in the literature of nudges, which are just, they're not providing any incentive. They're just giving you some extra information. This is actually a really, really large treatment effect for a relatively or very cheap intervention in this case, right? Like it's like a 6 percentage points over 30% baseline. This works really, really well. In 2018, the effect was actually twice as large. This is saying less about the intervention because these are also two different populations of colleges here, so I don't want to make too many comparisons here. But in general, this is seen as a very successful intervention. It is also highly statistically significant, so there's a lot of signal to find this average treatment effect. However, what I now want to shift gears to, of course, is rather than answering the question, does this work on average, I want to answer the question, can we find groups for which this worked better than for others? Or can we even estimate on kind of an individual basis based on information about a specific student, can I predict their likely treatment effect in the sense that can I estimate the conditional average treatment effect for people with similar characteristics? Yeah, Talia?
Do you know how many people opt out of text, like in the first text message?
So unfortunately in this data we don't have any intermediate outcomes, like do they respond in certain ways. I think that could help us to say a little bit more about what's going on here. We haven't tried to exploit this data yet, and as far as I know, it's not in the specific data set we have, but I think it would be a good question. Yeah, I think one weakness here is that it's really just a binary outcome. Yeah.
Why not just treat everyone if it works mostly?
Yeah, so that's a great question. I think you're pointing to, I think, two limitations here that I should point out, and so it's a good opportunity to do so. So first of all, we're going to use this to ask the question whether we can target better or not. Is this not the best application, I think, for targeting because it's a cheap intervention? You could nevertheless think that both heterogeneity analysis and targeting have value. The main two reasons that we are thinking about here is that you may not want to send texts that are ineffective because you're inundating people with text and making them less sensitive to future text. We're not explicitly modeling that, but that could be one reason. I think a second reason for heterogeneity analysis is if you found a group for which this really doesn't work, then you may also want to go out and understand why it doesn't work and find more expensive interventions for them and see this as a baseline. But I do think, in the end, we are seeing this mainly as a methodological demonstration here, where maybe the application of targeting is not the most important one in this case, but we hope to learn something about targeting problems in general. I still think heterogeneity here has relevance along the lines of what I just mentioned. But I think it's a very valid question. Great. So the idea is that maybe we can not only learn about average treatment effects, but maybe we can learn about treatment effects of subpopulations. And the reason why we can do so here is that there was randomization on a student-by-student level, independent of what their baseline characteristics are. So in principle, we can estimate treatment effects not just on average, but also for subgroups. And so the specific technology we're using, I'm just going to sketch this very briefly here, is we're using causal trees, as introduced by Susan Athey and Hideo Imbens, where we use a tree, but not in order to find groups where the outcome on average is very different, but instead to find groups where the treatment effects are very different. So if you're familiar with a standard regression tree, what this tree does is rather than partitioning the space so that at every step I find two groups where the average outcome is different, it just calculates the treatment effects in both of those leaves by estimating a treatment effect, like treatment group minus control group, for one group versus the other, and then it basically successively partitions the space into two groups at a time with as large of a treatment effect difference as possible, and then moves to the next level and then makes the partition finer. And so we're using this basic technology of finding nice trees in the data, but we're not just using trees, we're then combining many trees into a forest and using the causal forest or the generalized random forest methodology pioneered by Stefan Varga and Susan Athey, in which we are basically averaging over many such trees to get a better estimate of our heterogeneous treatment effects. And we're not just doing that, we're also splitting the sample a lot. So whenever I show you results, I will show you results based on having run our causal forest on one part of the data, and then evaluating it on a fresh part of the data that was not used to estimate heterogeneity. And the reason why I'm doing that is that we will always find that it looks like there's heterogeneity in the data we look at, because even randomly there will be variation in the treatment effect in subgroups, but we then want to validate that on new samples. And so everything I show you is based on tenfold cross-validation, where the evaluation always happens on 10% of the data, and we're then shifting around what these 10% are and averaging over those 10 splits. Okay, so this is basically the very quick rundown of the main methodology we're using here. What I want to discuss is the results we get out of that, the challenges we then run into, and how we address those challenges. So first of all, I can show you the distribution of treatment effect estimates we're seeing here. So as a reminder, this intervention on average had a treatment effect of around 6 percentage points. And it turns out that if we estimate treatment effects in this way, in order to approximate the conditional average treatment effect, then those conditional average treatment effects actually range from around 0 to around 15. So 2 pieces of good news here. The first piece of good news is that there doesn't seem to be anybody who had a negative effect. So it doesn't seem to be that this made it worse for anybody. This goes in the direction of, we should probably just send text messages to everybody. There's no reason here to believe that it had a negative effect. The second good news is that there seems to be quite some heterogeneity. So maybe we can learn something from that. But now comes the bad news, which is based on this graph, I wouldn't be able to tell you whether this is real or not, right? If I had pure noise, then I would have also seen some spread. And so just by looking at a distribution of estimated treatment effects, there's very little I can say. So one thing we could now do is do some statistical analysis of whether there is true heterogeneity here or not. Instead, I'm going to shift gears and say maybe we can evaluate that by how valuable that would have been had we used it for targeting, right? What would have happened had we, for example, used this estimate and only sent reminders to only the top 50% of estimated treatment effects? And so specifically, we're now moving from estimating this heterogeneous treatment effect to thinking about a policy that assigns people, and a natural policy to consider here to assign only to the people with the highest treatment effects, and then to vary to how many people are assigned that. Unfortunately, we don't know what the conditional average treatment effect is, so putting a hat on top, so the only difference here is that there's a small hat appearing on the tau. So I'm now asking the question, if I use that, I plugged it in, I gave treatment only to the top ranked people, how well would that do? In order to do that for the last 10 minutes of my talk, what I will do is repeatedly show you versions of this graph that I have on the slide here, where on the x-axis, I'm plotting the fraction of people assigned to treatment, and on the y-axis, I'm plotting the treatment effect, I'm plotting the overall average of people who renew by the deadline. So there are 2 numbers I can very easily explain to you. The bottom left number says that if everybody's in control, if I don't send any of the reminders, then 36.5% will renew their student financial aid by the deadline. If I assign everybody, then 43.5, which is the baseline plus the 6 percentage points, will renew. So this would be on the right. And now if I took a random subset, like I didn't use any contextual information, I just took a random 50%, then I would achieve exactly 50% of that and get to 40%, right? I would be on the diagonal if I chose a random number. And so the question is now, can I do better than this by kind of being the top left, where I assign a subset and achieve a high effect using that? So you could now ask the question how I can possibly do that, and that's the one slide of econometrics. So I'm now interested in evaluating some policy that uses the x and then decides the probability of assigning somebody. And I'm interested in evaluating the expected fraction that will renew by the deadline. Now, unfortunately, I can't go back and run an experiment each time. But the trick is that because I have a randomized experiment, I can back out from that data what would have happened under all these counterfactuals by effectively using a counterfactual estimator. And I'm just going to put this here. So this is normally where I apologize to my econometrics colleagues that I'm not showing enough formulas, but where I apologize to everybody else for showing these formulas. So basically, the idea is that in the same way that I can estimate an average treatment effect, I can also estimate an effect of the difference between 2 policies, because I get an unbiased estimator of the treatment effect for every x by kind of multiplying the outcome by this multiplier that is either measuring that somebody is unexpectedly in treatment or in control. And so this tells me that there is identification, so I can estimate those differences. And I can now implement that using sample splitting. So I'm always using out of sample data to get an unbiased estimate. And I can do that in a way where I'm using some additional machine learning parameters here to make this more precise, in a way where the unbiased estimate the guarantee that is unbiased only depends on the randomization and not that I chose the right machine learning method. So this is like a very informal way of saying we're doing something here that is robust to misspecification in my machine learning model. And because we have randomization, we can get statistically valid estimates of these counterfactual estimates. And we can also do inference on them, so I can also put standard error estimates around that. Yeah?
How should I think about, you're doing tenfold crossroad, and so all this is happening in the 1/10?
Yeah, so the way that I think about it is that I'm only using 90% to decide on the ranking, and then 10% to evaluate it. So in a way, what I'm really evaluating overall, and I'm doing this 10 times, right? It's like a ranking that is randomly assigning somebody to one of those 10 rankings. And then I get kind of a well-defined estimate here. So it's like I'm not really evaluating any one of those 10 rankings, but I'm kind of evaluating the average of that, which is equivalent to choosing a random of those 10 rankings. That's how I think about it.
Yeah, I guess my question was, so this estimate, the second estimate that you have to do on the sample splitting, like that estimate's going to happen on each of the, like the 1/10, right?
Yeah, that's happening on the 1/10. And so any nuisance parameter I'm using for that, I'm also never using that left out data. And that happens to be enough to get an unbiased estimate. I then need to do some extra work to also show that I can still estimate the variance, because there's not going to be correlation between those. But effectively what it gives me is it gives me one number that is an estimate of the treatment effect for every unit where I've only used data that doesn't use that unit, and then I can average that and I can calculate standard errors, and I have to show that kind of the covariance between different folds is second order to the typical variance. And so we're making that assumption here. So yeah, it's a good question. So this is basically a little bit the magic that I can do counterfactual evaluation. I should say, though, there is one important limitation relative to what you would do if you actually ran this experiment, which is I'm evaluating that on the same year that I have the data for, right? So this is a very optimistic view because I know by construction the distribution is not going to change. It's not like capturing anything where I use 2017 data evaluating in 2018, which we could try, but here there's a bit of a challenge because the treatments look slightly different and the colleges look slightly different, but that is something we could also try here. Okay, so this was like my attempt to convince you that the following numbers are more or less credible. So I'm now going to first plot what happens if I indeed do exactly what I just told you. I'm using the treatment effect estimates. I'm ranking people by those treatment effect estimates. And then I'm showing you, for example, if I assign 50%, then I'm getting to around 65% or 60% or so, in this case, of the benefit. There is also, and it's only faint blue shading here that you see on the screens on the side, 95% confidence intervals around that. They are pointwise. So this is like, for those of you interested in statistics here, this just means if you fix the fraction, that would be a valid confidence interval. Okay, so honestly, like we worked on this for a long time. It was a pretty messy data exercise. So this was very disappointing because this confirms that this thing is very, very noisy, right? Like there is no like big separation where we really found a few people who responded really well. But it looks like we found some structure here. It's statistically significant, so there's definitely heterogeneity here. But the effect doesn't seem to be that large of using this information. So we therefore thought about alternatives that we could evaluate. And here is something that we could have done in the first place without even doing all this causal complicated stuff. We could have just predicted, will somebody renew their student financial aid in the absence of our reminders? And then said, well, maybe we should send it to those people who don't already renew, right? Like the idea being that we should probably send reminders to people who currently don't renew, where I can predict that they won't renew. That has the advantage that now I don't need any fancy schmancy causal machine learning. I can just predict outcome on X in my baseline sample. So we can also evaluate this policy. And it turns out that this policy would do exactly the wrong thing. So if I used the 50% that have the lowest baseline and targeted, I would actually get less than 50% of the value, which we think is because the people who have a low baseline are actually also less likely to respond. Those may be the people that even if I send them the nudge, they will not respond, right? So this would have clearly been the wrong thing. But there's something extremely curious about this picture here. If you think of yourself like rotating this by 180 degrees. So you would have done exactly what you would have thought is the wrong thing. You'd have sent a reminder to those people who already are likely to renew. You would have actually done better than all of our fancy schmancy, to use the same technical term again, than all of our fancy schmancy machine learning, causal machine learning, right? So this seems to suggest that there is some information in the baseline about ranking people. We just didn't use it in the right way. And so this is kind of approaching the punchline here. So here's a third thing we did. We thought, why don't we use the baseline information and write the simplest economical model we can think of? So in this case, we assumed a simple choice model that leads to a logistic regression. So we're assuming that there is a logistic regression relationship between the treatment effect, so the outcome under treatment and the baseline, by effectively assuming that there's a logistic regression relationship that links the treated and the control, which is what you would get out of the idea that maybe there's a constant hassle cost in like a simple economic choice model where somebody just chooses between doing the treatment or sticking with the control. So in other words, what we did is we fitted a logit regression this may look complicated, but it's a very simple logit regression. I'm simply taking my baseline predictions, which are fully non-parametric. I'm using my machine learning to get baseline predictions. I'm turning those 0 to 1 numbers into -infinity to +infinity numbers by doing a logit transformation. And then I'm running a logit regression of my outcome on treatment and the score that I generated. So in other words, I'm doing a logit regression where I'm using the baseline prediction as my super feature. So this is the simplest, I think, baseline model of choice we could have thought about here. And then we are backing out what the treatment effects are from them and using that for targeting. Forget about the fact that we also consider targeting by enrollment. What I want to focus on is the yellow line here, which is the one on the very top. So this is using the simple logit relationship on top of a non-parametric machine learning one. So we think of this as a hybrid method. We are doing machine learning for what is easy to predict, which is the baseline. We're then running the simplest possible economic model on top. And that gives us a result that is about twice as good as our sophisticated machine learning method. If we use kind of some of the additional data that only becomes available later, it's even clearer. So here we now get like more than 75% of the benefit from 50% of targeting, or around 75% from 50% targeting, by kind of combining the complicated machine learning baseline, or like the machine learning prediction baseline, with this simple economic model on top. Yeah.
Going back to the predictive targeting, the negative baseline, did you also consider what would happen if you model what they would do under treatment, like you showed the result for under no treatment?
So can you say again what you mean? So what would happen if?
Like, if you targeted the people who are most likely to enroll if they got treatment? Because if I understood right, you were thinking about targeting people who are least likely to enroll if they didn't get treatment, right?
Right. I see what you're saying. So we did not try to do the prediction on the treated group, if that's what you mean.
Yeah.
So that would be interesting to do. The reason why we thought this is a natural baseline is that in a setting where we would normally think that you have a lot of control group data, and you may rank by that, therefore. We haven't actually not thought about using the prediction of the treated. That would be a good idea. We haven't done that yet. Yeah.
And does it beat the inverse of the negative baseline?
It does about the same. It does a little bit better. So the ranking is a bit improved, but I don't think it's a strict improvement. So if we have some graphs where we flipped it. I believe it does a little bit better, but it's not statistically significant. Yeah, so let me just conclude by kind of telling you what our interpretations of what's going on here and why we find this interesting in general, and we think it's quite generalizable, because we found again and again that these randomized trials are extremely noisy and it's really hard to good targeting. So here is kind of what's going on here. On the x-axis is the predicted baseline, and on the y-axis is the estimated treatment effect. If I'm using my non-parametric Kate, which is the top one here in orange, you see that, of course, there's variation in the estimated treatment effect, even for those that have the same baseline, because there can be two people who have the same baseline but still have different treatment effects because their treated outcomes are systematically different. If I'm using the simple logit from baseline, which is the dark blue one, you see that this relationship is very limited because I've imposed a simple functional form. I've assumed effectively that the relationship has to be within a very narrow parametric family. So it just turns out that using the simple blue relationship here does better than using the fully non-parametric one. And here we tried a few other things that I can talk you through if that's of interest after my talk, that we also tried out. But the main thing is that we could never beat this kind of very simple relationship. So what does a simple relationship imply? It kind of means it learns in a data-driven way from the data about both the treated and the control, about basically which part of the baseline to prioritize. And specifically, it says that the people who should be prioritized are those people with a baseline somewhere in the middle that were kind of 50-50 on renewing before. This is where we get most of the effect. While the people who either are already very likely to renew or are very unlikely to renew in the first place also have the smallest effects. You know, ex post, this sounds totally plausible. It's not something that we had thought about before, and we would have made a big mistake had we kind of gotten that wrong in the first place. So what's the kind of takeaway and why we think this is the case and why this is interesting? Our main insight here is that this baseline here is a first order thing that varies a lot between people, that varies systematically from around 10% to around 75%. It's something that is easy to predict using standard machine learning with a lot of variation. The treatment effects on the other side, they also vary, but they only vary, like we saw before, maybe between 0 and 12 percentage points, and the variation is much more noisy. So it's much easier in this case to predict this first order thing that has a lot of variation based on our limited and noisy data, while it's very hard to directly estimate this complicated, more noisy object that has smaller variation. And so we are doing better by basically using machine learning for the first task, but then using a simple economic model that imposes some reasonable structure on the second. So effectively, there's a lot of value in regularizing the heterogeneous treatment effect estimate, while we don't see any value or need to do the same with a baseline where we can go fully non-parametric, and that gives us a lot of ability to target better. And so, okay, again, let me just recap here and wrap up. The opportunity I was talking about today is to use machine learning to find subgroups with large effects and then target policies accordingly. The challenge that we've seen here, but we've seen in many other trials as well, is that these estimates are often extremely noisy. And therefore, we can hardly, like in many cases, it's hard to actually deliver on this promise. So the answers we give here is that we compare a number of ways of combining predictive inference with causal inference. And here, doing naive predictive inference doesn't work right. However, combining predictive inference with the right simple causal model is the one that does best in this specific case. And if you guys are interested in this, Ginny Ma, who is a great statistics student at Stanford, PhD student at Stanford, is working with Li Huolei and myself on like providing some theoretical foundations that shows when this effect is the case. And we have some first results on that. So thanks a lot.
We have time for one or two questions. Oh yeah.
Yeah.
Is the one lesson here is that conditional average treatment effect is relatively smooth function. So when we model that, we should put some restriction, whereas the baseline can be a lot more really going on that we want more flexible model.
So that's a great question. So the interpretation you're giving that it's because the heterogeneous treatment effect is a relatively smooth function of maybe the baseline, for example, I think is one interpretation. I'm not sure whether that's the right one. I think there's a more general interpretation that takes less strong of a stance, which is to say that the heterogeneous treatment effect is hard enough to estimate that even if it isn't really smooth, you're better off regularizing more strongly and estimating a smooth approximation of it. So I don't necessarily think we've learned something about whether the heterogeneous treatment effect has a simple form, but I think we've learned that it's not enough data to estimate that more complicated form, and we may be better off assuming what you're saying or using the same assumption simply for regularization. But whether that really means we've learned something about the structure of the heterogeneous treatment effects, I think of it more as like it's just really hard to say on relatively noisy data.
And there must be a way to do it one step. Is that correct?
Yeah, so you could in principle think about adding regularization in a single step. We found it easier to do it in two steps, where in the first step we predict some things that are easy to predict. So here I showed you baseline. We also did it, for example, with predicting enrollment, which is another thing that is easily measured and easily predicted. And then run a second step on top of those extracted features. I do think if you implemented that in a single way, maybe not using random forest, but using deep learning, I think there would be ways of doing that in a single shot. For random forest, we found it easier to do that in two steps. And then something I didn't show you is you could also, for example, run a causal forest in a second stage on top of those simple features, because now the complexity is not as large anymore and it works much better. But in all cases, the idea that worked best for us was to extract simple features and then run not too complex of a model on top of those. But I think the direction you're pointing out would be very valuable to think about further. Okay, thanks.